Hi, welcome back. This time we'll just see some fun exercise. So let's start with a definition. Assume we have a field K and now an absolute value on K is absolute value is defined just what you would expect it to be. So this is a map from K to the non-negative reals, and we want some conditions. So the first condition is that it should be 0 if and only if x is 0. So for x in K, let's call this map like this. And then the second condition is that the absolute value should be multiplicative. So it's a group homomorphism from the invertible elements of K to the positive reals. And then furthermore, we wanted to satisfy the triangle inequality. Okay, that's the definition. And now we want a further condition, namely we call an absolute value on K nonarchimedean. K is called nonarchimedean if there's a stronger triangle inequality, namely if the absolute value of x plus y is at most the maximum of the absolute value of x and y. Alright, and now we come to the exercise. So let me state it. So show that an absolute value on K is non-Archimedean if and only if the absolute value of n is at most 1 for all integers, for all positive integers. Okay, that's the exercise. If you want, you can try it like this and stop the video. Otherwise, I can give you a hint and also later the full solution. So I don't know how hard it is without the hint. I just know this one solution. So well, to come to this solution without the hint might be quite hard, but with the hint, the exercise is doable. So the hint is apply the binomial theorem. And well, if you want, you can try it with the hint and have some fun solving it. Otherwise, I'll prove it. So let's look at the absolute value of 1. So where 1 is just the 1 in the field. And now we apply property 2, the multiplicativity, and now we apply that it's non-zero for non-zero elements. So we get that if we divide by the absolute value of 1, we get that the absolute value of 1 is the real number 1. Okay, and now that we have that, we can look at the first direction, and this is in fact clear. This is just using this and induction. So we have shown that it's true for n equal to 1, and then we use the that it's non-Archimedean. Then we get the maximum of 1 and 1, and we just need to use induction. Now we come to the more interesting direction, namely we consider x plus y to the n. And what's that? Well, we can, well, at first let me write it like that, x plus y to the n by multiplicativity. So we get that it's by the binomial theorem. You can check again by induction that the binomial theorem generalizes to arbitrary commutative rings with 1. And so this is just adding up 1 this many times. So this also holds if the characteristic of the ring is non-zero. And then we have x to the n minus k, y to the k. And now we apply the triangle inequality, which we can do because we assume that it's an absolute value. So in fact, we apply it several times so that we get the sum. And then also we apply the multiplicativity, so we get the absolute value of x to the n minus k, the absolute value of y to the k. Okay, so we have that. Then the next thing we can do is, well, there are two options basically. We can take the maximum of the absolute value in x and y and raise this to the power of n. And what we also could have done, what we do now, is we can apply our hypothesis. So this is at most 1. So we get the maximum of, because it's a it's a non-negative integer, so x, y to the n. Well, then we just add this thing up n times. And well, now let's look, what do we have? So we have x plus y to the n is at most that. And now if we raise to the 1 over n, so take the nth root, then we get that x plus y is at most. And now we also can take the limit, because this holds for every n. So nth root of n, maximum of x, y to the n. Well, and what we also could have done earlier, but what we can also do now, is that this is maximum of x and y. Then we have the limit of n to the 1 over n. And this limit is 1, which you might know from calculus. So we are already done. So yeah, I quite like the interplay of algebra and calculus here. So in the end you use this thing here, and then you're done, and you can check that absolute value is non-Archimedean if and only if this condition holds. So thanks for your attention, have a good day, and see you next time. Bye.